So, the factors in a fermentation system which affect the oxygen supply rate or the oxygen transfer rate, this includes temperature, pressure, diffusivity, viscosity and flow parameters of non-Newtonian fluids. Like for example, there are certain fluids which may become like fungal fermentations or plant cell fermentations that may behave at high cell densities and non-Newtonian fluids. Then the density, surface tension, presence of surfactants, ionic strength of the medium, concentration of solids, power input, aeration rate and the geometry of the bioreactors. So, there are n number of parameters which can affect the oxygen supply rate or oxygen transfer rate. Now, generally what are the parameters which are manipulated or which are varied to make changes in the oxygen transfer rate in the reactor systems? So, of the various factors which affect the oxygen supply rate, we generally bring about the changes in the following variables which are as shown on the slide here. We try to increase the pressure, that will also increase the oxygen transport rate. We can increase the shear rate by increasing the power input, thereby again improving the oxygen transfer rate, which happens by the impellers, because the higher the rotational speed, they will break down the larger bubbles into smaller bubbles, but this may also increase by increasing the shear forces. Then the aeration velocity directly increasing will also lead to increase in the oxygen transfer rate. Now, the other parameters for a given geometry of the bioreactor depends on the nature of the fermentation process. So, as we have done it earlier, the oxygen transfer rate in bioprocesses, when we assume that gas liquid mass transfer resistance is the slowest step, or the gas liquid interface is the most crucial step affecting the oxygen transfer, then the oxygen transfer rate is defined as given here. Now, if this is so, and if we need to determine the value of KLa as shown here, then we generally use two techniques. One is called the gassing out technique, which is a static method. In this method, first the oxygen is stripped off from the medium by sparging in nitrogen, and then, so which means that all the oxygen is being purged off. Then air is sparged through the medium and the dissolved oxygen concentration therefore starts rising, and it is then measured as a function of time using an oxygen probe in the reactor. So, what we collect is the data of Cl versus time, and now this data is fitted in the equation which we had shown earlier of OTR, which is oxygen transfer rate, is so your OTR is nothing but dCl by dt, the rate of oxygen transfer. Now, why? Because here dCl by dt is the rate of accumulation of oxygen in the medium. So, because there are no cells present, so there will be no oxygen consumption. Therefore, the oxygen consumption term is not considered. So, whatever oxygen is being transferred in the medium defined as the RHS here will be equal to the rate at which the oxygen is getting accumulated in the broth. So, now if we integrate this equation given here, then it becomes a linear function as shown here. And if we make a plot of ln Cl star by Cl star minus Cl versus t, then the slope of that line can give us the KLa. There is another method called dynamic method, because this will give you a better approximation of KLa, because there will be culture growing inside the fermenter system. So, it is much closer to a real situation. So, the experiments are carried out in actual fermentation system. Initially, the system is maintained at steady state with respect to oxygen. Then, at some given time, the aeration is cut off, and what you will observe is the change in the oxygen profile with respect to time. Now, before the dissolved oxygen levels falls below the critical oxygen, again the air is sparged in, and the concentration of oxygen with respect to time is further noted till it reaches the steady state again. As shown on the slide here will be the trend which will be observed generally for Cl versus time. So, till the arrow which is showing here as air off, it is a steady state with respect to oxygen. Once the air is cut off, so there will be a linear decrease, assuming that during this experiment there is no significant growth happening. So, the x can be assumed to be nearly the same, constant. So, if Q0 is the specific oxygen demand, Q0 O2, and x is the biomass, this will determine the oxygen demand or oxygen uptake rate. Now, during this phase, when the air is cut off, there is only oxygen demand, but there is no oxygen transfer. So, the rate at which the oxygen in the bulk will be coming down, as shown here, will be linear, as Q0 O2 x is a constant. So, we can see it is a straight line, and this slope can give us the value of the oxygen demand. Before it goes below C critical, again the air is switched on and it will gradually reach to the steady state value. Now, during this increase, again data is collected for various CLN at different time points. Now, at every such point on this plot, we can take a slope which will determine the dCl by dt at that time with the corresponding Cl value and the time value. So, we will have such data with us. So, let us come to our continuity or mass balance for oxygen. So, if you see equation 1 here, this is simple mass balance for oxygen transfer. Your dCl by dt stands for the oxygen accumulation rate. KLa times Cl star minus Cl stands for the oxygen uptake rate, oxygen transfer rate, and RO2 times Cx, where RO2 is nothing equivalent to your QO2, which is specific oxygen demand, and Cx is nothing but your x. So, this stands for your oxygen uptake rate. Now, the first half of the experiment, which I am encircling here, the slope there will give us the oxygen demand of the culture, which is your oxygen uptake rate. Now, oxygen uptake rate from the slope can be determined. So, then this value is known, a constant. And if you do the rearrangement here of equation 1, so after rearrangement we will reach to equation 2, and Cl is unknown, rest all the factors can be obtained. So, dCl by dt is x here and Cl is y. So, it is again a linear function, and the rearrangement gives us the slope which is inverse of KLa. So, there are empirical correlationships also present for KLa determination. It is a function of physical properties and vessel geometry. So, the correlations are generally expressed by dimensionless groups or numbers, and they are also used in scale up of the processes. So, dimensionless numbers like Sherwood number, Schmidt's number, Reynolds number, Power number, Grashoff's number and Froude's number. So, one such relationship here can be used, has been used to determine how KLa can be a function of various other reactor operating parameters like the gassed power requirement, the volume of the reactor, superficial gas velocity, the RPM of the impeller. So, your equation 1 is one such empirical relationship to determine volumetric mass transfer coefficient. Now, if you notice, these relationships, they do not include the effect of medium composition. However, presence of salts, surfactants, they can also significantly alter the bubble size due to their effect on surface tension, which forms the liquid film resistance around the gas bubble, and thereby change the bubble size, which changes the surface area for mass transfer, and the thickness of the film changes, then it is also impacting the mass transfer coefficient. Now, these factors then eventually affect the oxygen solubility at equilibrium, which is the C star value. Similarly, your temperature and pressure, it can also affect both the saturation concentration of oxygen, which is your C star, which is governed by the mole fraction of oxygen, and also the pressure and KLa. So, let us see what are the functions of an agitator. We have seen during the introductory lecture that it can provide uniform dispersion of gas bubbles. It can produce small gas bubbles by breaking the large bubbles at the gas inlet by shearing with the liquid velocity gradient. Maximize the retention time of the gas in the broth by driving the gas bubbles to the bottom of the reactor. So, your axial movement can improve the retention of the gas bubbles. Maintains uniform concentration of the nutrients throughout the bioreactor. And it also facilitates heat transfer and maintains uniform temperature throughout the bioreactor. So, it also disperses the gas bubbles to the walls of the reactor. So, if you see on the slide, axial flow impellers have been shown here, where the movement is parallel to the shaft, and radial flow impellers have also been shown, where the movement is perpendicular to the shaft. So, examples well known for axial impeller is marine impeller, and for radial flow impellers mostly used are turbine or Ruston turbine impellers. Now, for adequate agitation, the power will be consumed by the impeller. So, how to determine the power consumption? This power consumption is found to be a function of various physical properties, operating conditions and vessel and impeller geometry. So, again dimensionless analysis is used to provide these relationships. So, if you see one such relationship, it shows here that the power consumed by the impeller, which is given here by the dimensionless number called as power number, is found to be a function of other dimensionless numbers, which are in turn a function of various reactor and vessel geometry and the fermentation parameters. Like the first dimensionless number is the impeller Reynolds number. Then the second one is your Froude's number, which takes into account the gravitational forces. The Reynolds number, we all know, it is the ratio of the inertial forces to viscous forces, and then rest of these are relating the geometrical parameters to the power consumed. So, now if you noticed, dt, which is the tank diameter to the impeller diameter, di, h is the height of the tank, di is the impeller diameter, dw is the width of the impeller, and di is the impeller diameter. So, these ratios dt by di, h by di, dw by di, these are generally governed by thumb rules and they can be assumed to be constant. So, we can neglect these, and for fully baffled vessels, the vortex, we will assume there is no vortex formation. So, further, the effect of gravitational forces, which is the Froude's number, on power consumption also becomes negligible. So, this is further neglected, and because, as I said earlier, the length ratios are constant. So, now effectively the power number is found to be a function of the Reynolds number. So, for different kinds of impellers, if a correlation is drawn with the change in the Reynolds number, how the power number changes, as shown here in a plot, you can observe the different profiles. In most of these cases, in the turbulent region where the Reynolds number is beyond 1000 or 10,000, the power number is found to become constant. At lower Reynolds number, your power number is said to be inversely proportional to the Reynolds number. And when power number is constant is the case, if you see here beyond 10,000, it becomes constant. So, if you see at very low Reynolds numbers, it can be considered as a linear drop, and therefore, it is said that the power number is inversely proportional to the Reynolds number. And at NREs in the turbulent region greater than 10 to the power of 4, your power number becomes constant for a given type of impeller. Like for example, for 6 blade turbine impeller, this number becomes 6.2. So, power number is given by an expression here where P is the power consumed, N is the RPM, and D is the diameter of the impeller, and rho is the density of the broth. So, then the power consumed by the impeller given at the given reactor operating parameters can be determined. This is for a single impeller. So, if there are more number of impellers, then this power consumed can be multiplied with the number of impellers to give the total power consumed by that system. Now, the power consumed by the impeller in a gas powered system will be lesser than the power consumed in an ungassed system, because to reach to a particular homogeneity, the gas sparging also helps in the mixing. So, the net power consumed therefore is less. So, net power required by the impeller operating at the same speed in a gas free liquid, let us assume it is at PM0. So, then the correlation given here at the bottom is generally used to relate the gassed and ungassed power requirement with the functions of aeration number, Froude's number, Reynolds number and your linear ratios of your length ratios, where it is di by dt. dt stands for the tank diameter and di is the impeller diameter. So, as I said earlier, the linear length ratios, they follow thumb rules. So, here these are some thumb rules given for reference, you can make note of it. In the given schematic, you can see capital D stands for the tank diameter, small b stands for the width of the baffle, your L is the length of the reactor or height of the reactor, small h is the height of the impeller, W is the width of the impeller and D is the diameter of the impeller. So, these linear dimensions or linear lengths have been related as constant ratios.